Swayam Prabha. Digital India. Educated India.
Now, we are going to discuss the transformation. The transformation is actually, if you know very well about that matrices and vector spaces, based on that the requirement is how to transform from domain to codomain, and then what are all the translation from mapping from domain to codomain with one-to-one on to bijective and so on. So, based on these areas we have to rotate the map, that is you take the image from the domain, you have to rotate it and translate it how it works. That is most important for AI and ML. Now, let us start with some introduction of the standard information. These are all the objective, that is based on rotation, translation, scaling, shear. Based on these four, we require to map from domain to codomain. That is what we would have been come across, that bijective, injective, surjective, all the mapping and so on. Now, next idea is derive homogeneous coordinate transformation matrices, and how to learn to build arbitrary transformation matrices from simple transformation. So, the transformation maps point to other point or vectors to other vectors. So, this picture shows that if you take a map P to T of P, so that it may be represent Q of T of P. So, you take a point from the domain and it maps to the codomain, it will go to the Q, that Q is represent T of P. So, actually what it represent the transform from domain to codomain, so that V equal to T of U will come. Now, we have to do with next idea is call it as affine transformation. So, affine transformation is based on line preserving characteristic of many physical important transformation, that is based on rigid body transformation, based on rotation and translation, and next one is scaling and shear. Now, let us go with another point that is important in graphics, is that we need only transform end points of a line segment, and let implementation draw line segment between the transformed end points. So, this is the map from domain to codomain. You take a point U, under the transformation T, it will go to T of U, and if you take a V, under the transformation we have to go to T of V. So, this is the pipeline from domain to codomain, or input to output, or mapping from domain to codomain, or independent to dependent. So, wherever you need application from point of view, you can apply it, and rasterizer, we have a buffer, and then that may reaches to T of V. Now, if you represent in terms of the graph, you take a vertex U, and then it will go to the T of U as a mapping. The T of U actually represent in terms of the pixels, then T of U and T of V as a pipeline to implement the transformation. Next, notation. So, we will be working with both coordinate free representation of transformation and representation within a particular frame, and if you P, Q, R be the point is in an affine space, U, V, W be the vectors in an affine space, alpha, beta, gamma are the scalars, P, Q, R represents of points, and make an array of 4 scalars in homogeneous coordinates, and U, V, W represent the points and array of 4 scalars in a homogeneous coordinates. Now, the translation is move a point to a new location. So, that you have to do translate and displace. So, the displacement determined by a vector d, that is 3 degree of freedom, and p dash is equal to p plus d. So, this is a technique you have to do with simple line segment, that is point to point make a line segment. So, that p dash equal to p plus d. And how many ways we can do that? So, this object, if you translate, so every point displayed and then the picture represent in the same way, that is you take cuboid and then that cuboid is represent from the domain to codomain. So, that will be translate from this. So, we can move a point to a new location in infinite ways. When we move many points, there is usually only one way. Now, translation using representation. Using the homogeneous coordinate representation in some frame, let P be the point of a 3-dimensional effect of this and extended to 4 dimension. Therefore, P x y z l are 1, and then P dash is equal to x dash y dash z dash 1, and operator with respect to the all the axes, call it as dx dy dz, and the 4th dimension with respect to time in no operator, therefore 0. Therefore, hence P dash equal to P plus D, or x dash equal to x plus dx, y dash equal to y plus dy, and z dash equal to z plus dz. So, this is the what we notate the expression is in a 4 dimension and x plus point equal to vector plus point. Now, we can translate into the matrix as the expression of the translation using 4 cross 4 matrix, because 4 dimensional representation. So, the matrix T in homogeneous coordinates, therefore, P dash is translate to P, therefore, TP, and then the matrix T2 T of dx dy dz, corresponding matrices as 1 0 0 dx for x, 0 1 0 dy for y, and 0 1 0 0 1 dz for z, and with respect to the 4th dimension we have to put it 1. So, this form is better for implementation, because all affine transformation can be expressed this way and multiple transformation can be concatenated together. Now, we have to rotate. Rotation is based on, see, this is the graph what we have to take, we have taken in the Cartesian plane to the polar form. So, x axis and y axis, if x represent r cos theta and y represent r sin theta, if you go with x to x comma y and x comma y to x dash y dash, then start from x equal to r cos phi and y equal to r cos sin phi. So, with the help of the polar form, and this will be translated to x dash y dash, then it will go to the x dash as x cos theta minus y sin theta, and y dash as x sin theta minus plus y cos theta. So, this is a rotation with the help of the 2D effect, and generally we denote x dash y dash is r into cos phi plus theta, because cos of a plus b equal to cos a cos b minus sin a sin b, and combine them and substitute this, you can get it x equal to r cos phi plus theta, that is cos of cos phi cos theta minus sin phi sin theta, you know r into this. So, r into this also will come here, because common to all, you know r cos phi equal to x. So, r cos phi substitute x, so that the problem reduces to x cos theta, and r sin phi is y, and with minus sign is there, therefore, y into sin theta will come. So, this way we can go with of all these things. So, the polar coordinates we can write in terms of the rotation x dash equal to x cos theta y minus y sin theta, y dash equal to x sin theta plus y cos theta. Now, the rotation about the z axis, in 3-dimensional leaves all points with the same z and equivalent to rotation in 2 dimension in planes of constant z. Therefore, x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta and z dash equal to z are in homogeneous coordinates p dash equal to r z of theta into p. So, this way we can represent the affine transformation in terms of the Cartesian as well as polar coordinate. And we have a rotation matrix r z of theta is, see this is cos theta minus sin theta, rest of them will be 0, and here sin theta and cos theta, rest of them will be 0, and we have a unit matrix 1 0 0 1, and if it is 4 cross 4 you have to write like that, and this way we can enlarge to n cross n. Now, the rotation about x and y axis, same argument as for the rotation about z axis. For the rotation about x axis, x is unchanged. For rotation about y axis, y is unchanged. Therefore, r of x comma theta equal to 1 0 0 0 and then 0 cos theta minus sin theta 0 and 0 sin theta cos theta 0 and then 0 0 1. So, this way we can represent the rotation about x axis. Similarly, the rotation about y axis is cos theta 0 sin theta 0, 0 1 0 0 minus sin theta 0 cos theta 0, 0 0 1. So, this way we can do for rotation about x axis and y axis. Now, this is a scaling, expand or contract along each axis the fixed point of origin as x dash is x suffix x of x, y dash equal to sy of x, z dash equal to sz of x and p dash equal to sp. So, the mapping is corresponding to picture. If you go there and then the reflect will be the scaling corresponding to x2, rest of the axis will be demonstrated. And then we have a S scaling of general idea is only the diagonal elements will come, above diagonal and below diagonal will be 0. So, this may rotate with the fixed point of origin, can view the image and corresponding matrix representation we can do like this. Next, if you have a reflection corresponding to negative scale factors, in that case s suffix x is minus 1, s suffix y equal to 1, then the mapping comes like this. So, this is the original reflect. Suppose s suffix x is minus 1 and s suffix y is minus 1 and then we have an image like this. So, that is what inverted and that will be the what the picture reflected from domain to codomain, and we have a corresponding negative scale factors of the function for Sx equal to minus 1 corresponding Sx equal to 1, Sy equal to minus 1 and also reflect in the minus 1. So, this way we can do with the scaling function. And then coming to the point of inverses, although we could compute the inverse matrices by general formula, we can use simple geometric observation, call it as a translation. The translation is nothing but the inverse of T inverse of dx, dy, dz, and corresponding we can write the translation as T of minus dx minus dy minus dz. So, this can represent the translation from domain to codomain, and we also notate like this. Suppose we have a rotation r inverse of theta, then we have r of minus theta. So, this may holds for any rotation matrix. So, note that since cos of minus theta cos theta we know it is a even function, sin of minus theta equal to minus sin theta is a odd function. So, based on the rotation also we can fix with the corresponding trigonometrical aspects of the one domain to the codomain, and we can easily incorporate with the orthogonal orthonormal ideas, and it will be very helpful to understand the norm of the vector, orthogonal of the vector, orthonormal process of the vector. Similarly, we can go for R inverse of theta, which is equal to R transpose of theta, means the scaling S inverse of Sx, Sy, Szz is S of 1 by Sx, 1 by Sy, 1 by Szz. So, this way we can convert to domain to codomain, and corresponding inverse function we can evaluate from the domain to codomain. Now, we have to do concatenation. We can form an arbitrary affine transformation matrices by multiplying together rotation, translation and scaling matrices. Because the same transformation is applied to many vertices, the cost of the forming of the matrix M equal to A, B, C, D is not significant compared to the cost of computing MP for many vertices P. So, the difficult part is how to form a desired transformation from the specification in the application. Now, order of the transformations. Note that the matrix on the right is the first applied. Number 2, mathematically the following are equivalent. If you take P dash, then A, B, C and to P can be written in terms of the associative property A of B of Cp, and then B of Cp calculate it and multiply them with A, so that P dash will be reflected. Therefore, the order of the transformation easily can calculate, and already we designed the affine matrix like that. Using that you can get it. Note, many references use column matrix to represent the points in terms of the column matrices. Therefore, P dash transformation equal to P transpose, C transpose, B transpose, A transpose. That is, if you have a P dash equal to P C A B C P, then you have to say A B fold transpose equal to what? B transpose into A transpose. The same way, if you take P dash equal to A B C P, the fold transpose, then what you have to do? So, first you have to, last one is first, and then third one is second, and second one is second, and third one is, first one is last. So, this way we can do with the inverse transform the same technique what we have to apply, what we have applied in matrices in the inverse transforms, the same thing we have to apply to here also, and you can easily understand. That is why matrices is most important. Now, we will go to the rotation about the origin. You have a what, a 3-dimensional axis, x axis, y axis, z axis. Suppose you have a vector along with I direction, j direction, k direction, and you have a vector and having the rotation like this. Now, the rotation we required, ultimately we required angle. So, the rotation by theta about the arbitrary axis can be decomposed into concatenation of rotations about the x, y and z axis. Therefore, we have r of theta equal to, with respect to z, r z of theta z, and r I of theta y represent corresponding to theta y. R x of theta x is represented to corresponding x axis of the rotation. Now, what we can infer it, if theta x, theta y, theta z are called the Euler angles. Euler angles mean this for honor of him they written as a Euler angle, and note that the rotation do not commute, we can use the rotation in another order, but with the different angles. So, that is the symbol we have to denote with the affine transformation of rotation. Now, the rotation about a fixed point other than the origin, move fixed point to the origin and rotate. So, we have m equal to t of p, r of theta and t of minus p. So, that we have a first one is rotation like this. You have to take a 3-dimensional effect. So, the cuboid you have to take it. The cube may be represent the p with respect to all the axes, and we have to transform to what? A, B, C, and then P is a matrix. So, this is the pictorial representation of transform from domain to codomain. In this way, we have to rotate with a 90 degree, 180, 270 and 360, so that the mapping will be easily identified. So, this call it as affine mapping. Now, for instancing, in modeling we often start with a simple object centered at the origin and oriented with the axis and at a standard size. What are all the things required is scale is required, orient is required, location is required. So, we apply the instant transformation to its vertices to scale, orient and locate, and then we have a mapping like that. So, let us start with the one x axis, y axis, and we have the picture of apple, and we have to transform, and we have to reflect that the transform is shifted to origin and it moves like that. And then if you do it with R reflect, corresponding the same picture can tilted and then picture reflected, and we have to do with the help of the size, and then it will reflect like this. So, like that we can do with the help of the matrix in terms of the TRS technique of a scale, oriented and locate, so that we can easily capture the picture of what domain to the codomain. Now, we have a shear. The shear is helpful to add one more basic transformation, that is equivalent to pulling faces in opposite direction. Therefore, this is a picture where the shear happened, where it has been pulling with either with the z axis or x axis or y axis. So, all the ways it having the shear, then how to attack the problem. Now, we convert into matrix. Consider simple shear along the x axis. So, x dash equal to x plus y cot theta and y dash equal to y, z dash equal to z. Then we can represent in terms of the what Cartesian plane x and y, and we have an angle of theta, so that it will reflect x dash comma y dash, and it may having the images pre-images x comma y, so that this represent in terms of the triangle, right angle triangle forms. So, this way we can do with shear from the x to y, and we make an angle of theta, and x dash can tilted to x plus y cot theta will come, y dash remain as it is, z dash remain as, because we are using only x and y and z is not touched, therefore keep as it is, and moving towards the y it moves like that. Then corresponding h of theta is 1 cot theta 0 0 from the first equation we can write in terms of the matrix. Second equation, there is no x axis and no y axis, no z axis, y axis only there, therefore 1 we have to put it. For third line of the matrix is no x, no y, no corresponding fourth dimension, therefore z only there, therefore coefficient is 1, and we are putting the fourth dimension, therefore last we have to put is 1, so that we can convert into the given linear expression in terms of the matrices. So, this is called as affine matrix. So, affine transform to affine matrix we can do that. So.